So I was supposed to be scheduled on the track for the bad things, but I had to move it earlier. So this is the bad thing and not the good thing. So here the idea is to make a small summary of my experiments with Circt-HLS. So it's just the presentation of how to use all that as a user. So I tried to use the tools that were implemented in Circt. I will present what it is. And I met many issues, many failures, and I just want to make a summary of that. So maybe I've done some stupid things, probably, but this is just my experience. So first of all, so I will talk about Circt-HLS. So I will present what is HLS. So that's working. So HLS stands for high-level synthesis. The idea is to generate some hardware based on behavioral description in a high-level language like C, C++. So the idea is to take some C++ code with most of the time data-intensive application, loops and things like that, and to transform that into hardware in a hardware description language. So the idea is to stop writing with HDL, hardware description languages, and to use the behavioral description to generate the hardware automatically. And currently, there are some commercial tools that are doing that very efficiently on data-intensive applications. So, for example, there is a Xilinx Vitis HLS tool and Montauk Catapult HLS tool. And for my research, I would like to have an open source tool which I can modify and which is efficient enough to have good results on the hardware accelerators. So in my research, I use high-level synthesis for several purposes. So the first one is the most classical one, is to synthesize accelerators. So I use that for tutorials, for courses on high-level synthesis, and also during my PhD for doing some hardware acceleration of dynamic binary translation. More recently, I've also tried to see how we can use high-level synthesis to synthesize microarchitectures. So the idea was to describe some architectures, like, for example, VLIW or pipeline processors at the C++ level, and to see if the HLS tool is able to generate hardware which is close to what we would do manually for designing a processor. And the result is that the C++ code is very control flow dominated. It's not exactly what tools are used to see, but it works and we can generate good enough processors for that. And the last things we are doing is speculative loop pipelining. So the idea, again, is to try to improve the performance of high-level synthesis on control-intensive applications. And what we propose is to do some speculation when we are doing loop pipelining. So sometimes if one of the paths is long and another one is short, is to speculate that we will use the result of the short path to start the next iteration. So just to say that
I understand the first two cases, but I don't understand why HLS is useful for speculative loop pipelining.
We want it's speculative loop pipelining to generate speculative accelerator.
Oh, you want to synthesize
on hardware, yeah.
Hardware for speculative.
The pipeline is to generate the accelerator. Yeah, is that. And so basically what we did is just to generate a loop transformation that removes some inter-iteration dependencies by speculating that there is no dependency, and all the control logic to do some rollback and to replace the iterations that went wrong. And as we wanted to generate hardware from that, we had to use a tool that we are developing in the team, which is called JCOS, and then to regenerate C code, which then we give to Vitis. And we hope that Vitis will understand what we did, and will be able to generate efficient hardware with the ugly C, C++ code that we have generated. So for this last one, again, it would be easier to feed a custom HLS tool and to be able to say to the tool what we know about inter-iteration dependencies and all that. So for all of these projects, an open HLS tools will be a plus. So what is MLIR? I have to do that slide. So MLIR is, as you probably knows, multi-level intermediate representation. So it's a tool for designing new dialects, which has different level of abstraction and which can be used to transform your application and to generate binaries or hardware in some projects. So here I've made an overview of several IRs used in MLIR to synthesize from ML applications into assembly. And the idea is that you will have some languages that are categorized into several axes. So you have, for example, on the left side, things that are more dedicated on what we want to do, which operation we want to do. And on the right side, more on the how to do them, the structure of the code. And then either you represent the memory as tensor or as buffers, memories, operations like we do in typical compilers. The only thing that you have to remember here is that there are many intermediate representations with different level of abstractions, and that we can navigate between these representations. Then, on top of that, there is another project which is called CIRT. So CIRT stands for Circuit Intermediate Representation Compilers and Tools. And the idea is to build upon MLIR some dialects to represent hardware accelerators, to build and transform hardware accelerators. So here they define many different groups with different abstraction levels, which will be used to generate verilog at the end, so to generate hardware description language. So the idea is that from the upstream MLIR dialects, you can generate several high-level hardware dialects, which can be lowered into the core dialects. I will present them later. And then you can use these dialects to generate system verilog and to use the standard commercial exit flows after that. And everything is open source, and we can find and modify all these different dialects, transformation, optimization that were developed. So I will present a bit more the different dialects that I used to go through my tests. So yes, it's promising for my need. So here I've put the different dialects I went through. So the idea is to have both some dialects in MLIR to go from C, C++ into the core dialects, and then some CIRT dialects which are able to go from these core dialects into hardware. And I've made different levels. So there are some high level in MLIR, low level, and then you have the high level hardware, which is still lower level than MLIR, the mid level hardware, which is the core dialects, and then the low level for generating system variables. And I will go through these different dialects. So at the highest level, you have the front end, which are used to translate the C, C++ into something that looks like MLIR. So most of the time we use polygase to get C++ into MLIR. So as we said before, it's not probably the best way to enter MLIR. That's the only one I have. And another way to get into MLIR was to use a PyTorch frontend to convert the PyTorch script into something that is inside MLIR. So here you will have the constructs that are higher level. So for example, you will have a dialect which represents PyTorch operation inside MLIR. Yes?
Question here. So do you see a shift in interest of HLS users from writing like imperative code to using more domain-specific graphs of operations?
Not me. I guess people are
what people want. Like they want, like for while loops, I guess you still have to, like speculative pipelining, you still need.
Yes, we still need to do C, C++, but for people, it's hard to say. I think that people that are doing machine learning, they could use some DSL. It will be easier for them. If you're in a very specific use case, it's always better with DSL. It's better for the people that write the accelerators. It's better for the people that write the compiler, I guess. So yeah, it's a good way to go. But still, you limit what you can, but you don't have to choose. Yeah.
Yeah. Since you wanted to start with C++, is there you don't want to rewrite your processor, the backend processors into this?
Yeah.
Do you have a content? What's the status of contents that on C++.
You mean Polyguest?
That's a C++.
Polyguest is the front end, so it reads C++
Okay.
and it generates MLIR.
But not
Sometimes.
Why not? Yeah. So what we have on the right is not.
No, it's the example for Python. Yeah. So then once you enter MLIR, you have different high-level dialects. So for example, you have one to represent linear algebra operations, another one to represent some tensors types and to do some operation on tensors. And the idea of these highest level languages is to represent what you want to do with at the highest level of abstraction so that you can keep the semantic and enable some transformation on that. For example, you know that you are doing matrix multiplication on your data, so you may have some specific transformation that you can do on that operation because you know what you aim to do. It's more interesting than just for loops that are doing the matrix multiplication. The last high-level dialect that I described here is the affine one, which is for the dialect for polyhedral compilations. This is what Polyguest generates most of the time. So the idea is to have some affine for loops, some affine memory access, affine expressions, so that you can do some polyhedral compiler transformation, what you used to do, and then lower this affine dialect into some lower level dialects to generate then assembly and design. So the low level things, for example, you have a low level dialect, which is here for representing vector operations. So the idea is to have something that is generic and can be lowered into any vector ISA extension. For example, the vector dialect can be lowered into ADE, SSE, and things like that. So it's to be target independent. You have a dialect for representing memories and memories operation, for example, for representing allocation, reallocation, mem copy, and all the operations that you can do on your memories. And then the standard control flow, so simple control flow, so the dialect for representing all the operations that you might have between the block of operations. So loop, while loop, turn, yes.
I'm not a user of MLIR.
Me neither.
All these dialects. So maybe my question is very naive, but so you're mentioning a couple of dialects. Are they going to combine well to compare?
All of these are there.
Yes, they are supposed to work well together. At the same time, you can have many different dialects all together in the same intermediate representation. You can lower some of them into something else. And the idea is that all the errors that you have, I go back, all the errors that you have here are some lowering transformation that you can do. So you're supposed to have a transformation that lower a vector into AVX dialects. And all the idea is to have an intermediate representation with different dialects live at the same time and to define some transformations that are working on your dialect. And to hope that everything is working.
Of two dialects, another dialect, or do you have to manually say how you transform each of the dialects? And lower each of them.
You mean when you are using it or when you are developing it?
Where you
as a developer, you can, if you want to enable the lowering from one dialect to another one, from your dialect to another one, you have to define functions for lowering all your operations into existing dialects. As a user, you have, when you list all the transformation you have on your compiler, you have like maybe not thousand, tens of the lowering possibilities, and you have to call the correct one and to lower the dialects into another one and to hope that you will get rid of one dialect to go to lower level ones. And as I will say later, it's not always that simple. Okay? Okay, so that's for the MLIR dialects. So then you have the highest level hardware dialects. So here, one of the dialects is for Calyx. So Calyx is a tool for a compiler for optimizing hardware. So they have their own intermediate representation, and as they wanted to be used, to be more visible, they developed a dialect in MLIR so that we can easily navigate from MLIR into Calyx tool and then go back to MLIR. So they already have their tools, they developed a dialect so that we can easily navigate from the Circt infrastructure into Calyx infrastructure. There is another dialect here. I described the uncheck, for example, for defining some fork join operation. It's used for CAN process network on patching heads. And the last one is VRTL. So it's maybe the most mature dialect in the Circt tools. This is the one used to lower the chisel into verilog. So chisel is a hardware construction language, which is developed. It's Scala, and it's used to some latest processor development in Berkeley are done using chisel. So this is the most used part of Circt, so maybe the one that is working the most. And this is not the one I use.
Doesn't it include the other one? Do you have functionality in handshake that is not included, that you cannot express included?
I could not say, I don't know. I think that, I don't know if there is any fork join IDs in here. You already described the registers and the combinatorial logic, so you don't need it, I guess. I'm not sure.
It's more like RTL concept.
Yeah, it could be put there. So then you have the three core dialects of Circt, which are here to represent anything that you want to represent with standard hardware description languages. So you can define some RTL blocks, you can instantiate them, and then inside those blocks, you can easily do some combinational operations, and you can define registers, which will be updated at each clock cycle, and so on. And then these dialects can either be lowered into LLA for low-level hardware, which is here to simulate your accelerators inside the Circt ecosystem. And then you have another dialect, which is here for generating system verilogs. So the idea is to go all the way into something which is strictly equivalent to system verilog, and then you can syntactically lower into system verilog. And then you can go back to the existing commercial toolchain to go into real hardware.
Maybe just a quick comment for the SSA people in the room. The blocks in MLIR can have the regions can have a dominator property enforced or not enforced. So if you care about imperative execution as a backend, you want to retain some domination property and ordering of instructions that is compatible with the data flow of values. If you're into circuits or into synchronous languages like data flow languages, you just lift that restriction. But then you cannot do arbitrary things with control flow anymore.
So this is the graph region where you're
Yes, well.
Yes.
Can you go back to the
Which one?
the previous, this one? You're saying time as a time system?
Yes, I knew that was that big voice question. I see that written somewhere. It's just for raising question, but I don't know exactly what I could say about that. It was advertised on the dialect, but I have to see more specifically what it means and what they did there.
I think the model time propagation is that.
It's like timing constraints that are enforced by
I think that this kind of thing is for maybe for seeing cycles for the simulation.
If I can add something, here I think time values are used to express time constraints directly in the data flow of your SSA program. So for example, here you see that the last line depends on parameter T. And so T needs to be defined before someone can act upon T saying, okay, I need to create a new time value from this one. And so you create this ordering from the diffuse chain of time values.
It's all related to the the fact that the semantics of hardware is we have no beta semantics and event-based simulation, discrete event simulation. So you need to express the time. But yeah.
Yeah, you can discuss. So this is for the theory of all the dialects and everything that should happen normally. And now what I try to do. So the idea was to be able to synthesize C, C++ into hardware easily as what I did with VT-HLS tool, for example. So as a user, I just want to feed my C, C++ file and to get some hardware. Maybe getting efficient hardware, but that's a second try. So I found a repository which is called Circt-HLS, which is supposed to be a combination of different projects enough to build a full HLS toolchain. So in this project, you have a reference to the Circt project, so all the dialects I just presented, the polygaze frontend, the calyx compiler for optimizing the accelerators, and they propose a full path from C, C++ into Verilog. And they also provide some scripts for doing all the lowering, all the different lowerings and generate automatically some hardware. So the idea is to use polygaze as a front end. Then inside polygaze, we generate some upstream MLIR dialects. And those dialects can be lowered inside Circt to generate some calyx IR, which is fed into the calyx compiler, which is able to regenerate the core dialects in Circt, which is lowered into Verilog, and then we have the hardware accelerator. So the good news is that the proposed tutorial on the GitHub is working fine. So it was a simple accumulation on a for loop. So everything works correctly. I can see all the different MLIR files with all the different level of abstraction, and I generated hardware. I don't know if it's efficient hardware, but it was a question. Then, as it was working, I said, okay, what I want the most is to be able to synthesize my processor using this toolchain. Okay, so a mistake in my animation. So my main goal is to be able to synthesize Comet, which is a pipeline processor that I talked earlier, from C++ into hardware. So here I faced a first issue is that in my code, in my C++ code, I use a lot of AC ints, which is types with configurable bit width, which are used a lot for in HLS. And these types are not easily parsed in polygaze and generate some ugly things at the entry MLIR level. So it cannot be lowered into something existing. I did not manage to lower that. So, okay, I'm ready to do some modifications in my C code. So I've removed all those AC int things, and I just used ints, some mask, and some bit shifts to get rid of all that.
Sorry. Where is the problem? Is it in the declaration, C++ declaration of AC int, or is it in the?
The city is the library.
Because it's a black. You didn't want to change the AC int implementation source code.
Yes,
It's
a
big
huge library file.
Yeah, so that.
It's a big page. So,
Yes.
but
It's working. It's able to parse it, but then it generates some ugly MLIR file.
But it's only ugly in the first place.
Probably.
It's already ugly.
I don't say that this is because of polygaze that it is ugly. But the fact is that the automated flow could not lower it where I wanted to go.
so it doesn't work. At some point it works.
Yeah.
You're still able to get the MLIR representation of the expanded templates corresponding to SAE.
Yeah.
And then the tool was not able to deal with it.
The problem was the idea of if you don't go where the tools were intended to go, you will do some buzzing things, and I think that was not intended to be done. So it highlighted some bugs and it was not working. So I prefer to get rid of these types than modifying polygaze.
But that's
No, I don't think polygaze can be fixed for those type of entries.
That's not the idea.
Yeah, it's not the idea.
but,
You need better H file.
there's also a C++ effort to have this as part of this. I mean, some kind of variable length.
I could not say.
There's something interest on that, but it's not clearly would be supported by colleagues.
And also, so my students did start from Seattle. And in Seattle, you have this you have the types.
Yeah, but then if you start at Seattle, it's no longer.
Yeah, so there's no path from Polyguys to Seattle. No,
No, the idea is just to. It's a chisel toolchain, so the idea is just to start from chisel. So you already start from hardware description language. So it's not really So once I got rid of all these types, which were
So you said you were using ACInt, which is a big header file with a huge template and lots of complicated C++ things. Isn't this a case for going to something like Albert discussed, some kind of a DSL, which would be able to express these kind of functionalities? I know there is bitint, which is coming to C23 and maybe and 2035 we will have support in every major one. So do you think you were limited by the toolchain or maybe the language or the flow that is following Polyguys?
maybe the theory.
Yeah, not exclusive.
Sure that if I could define a variable bit with types directly in C++, if these are handled correctly by Polyguys and by the tools, yes, that's the best case.
You probably should hack Polyguys to add support for these sometimes.
I think that this is how it is done in existing tools. They know their types, they distribute the ICInt.h file, and they know that they are handling them correctly. So it works, and it works pretty well in existing tools. But I don't know what the best solution would be. Maybe DSLs would be fine, but then you lost some expressivity.
In principle, your code modified after this green change is less readable than it used to be. I mean, you've lost something. Are you happy with this modification?
It's not that bad. It's not that bad to get rid of ICInt. It's more difficult to read, but
you hide it through macros or how do you do that?
No, manually. I already have some C code for doing instruction decoding using bit shift and mask. So I just found everything I needed and put it inside. Maybe there are some bugs, but
You've lost.
I don't care.
It doesn't work anyway. So
Yeah.
That's the kind of things that you want to avoid.
So what do you think you use semantics? Because yeah, use semantics. That's right.
This fits on the edges.
Yeah, but this is going to be inferred back by the.
Yes. As you always use mass, I guess that the tool is able to see that you don't need some bits of I think
that's what MLIR is supposed to make easier.
And actually, if you look at how it's implemented, the variable bit with the data type, it's just doing some masking. So it's doing exactly the same. But it's even inside some ugly thing, and the tool is not able to.
Well, it's clear with an infinite amount of time, you could have something that only goes down and not raise the instruction again, but if it works.
So then, when I managed to do that, I got the second issue is that I got many errors on my code about arrays being different, that arrays with a fixed size being different, that array references.
Because it's true.
Because it's true, yes. On my previous tools. And then I tried to get rid of that and to build something that is accepted by the compiler. So maybe I missed some information, but here I could not manage to do that. So it means whatever the modification I've done in my arrays and how I use the array that I was defining inside my processor, at some points, it raises that it's not compatible. So
Can you be more, can you give us more details? So what do you mean by,
So in my processor, I define a huge array which is used for data memory, for example, and at some point I define it as an array because I need to have a fixed size instantiated into hardware. And then when I call a function that can work on that memory, I pass it as a reference, which works when I compile it with a standard compiler. But here it was saying that it's not the compatible types.
if you rewrite your code so that you pass the.
I tried many different things. So to do some advanced passing it as an array, having a reference all the time. But at some points it was always failing. Okay. I guess there is a correct way to do that. I just say that I've not found it. Yeah. And that commercial tools were more friendly with me than. So here my guess was, okay, so synthesizing comment might be too challenging. Maybe we'll try some other paths to generate hardware. So the idea was, okay, on the Circt main page, they advertise a toolchain to generate efficiently PyTorch into hardware. And I was saying, okay, people are doing machine learning, people are trying to accelerate machine learning. So I guess that this path for Circt will be working a bit more than the one I was using. So here I tried again. So the first thing I needed is from my PyTorch script to generate some MLIR dialects. So here I made some research and found a tool which is called the Torch MLIR, which is aimed at translating PyTorch scripts into MLIR dialects. So here it adds even more dialects inside the flow. So now the script will be converted into Torch dialect, which is the MLIR dialects for representing Torch operations. And then this one is lowered into linear algebra, arithmetic, tensor, and control flow operations, which are classical in MLIR. And then the idea was to lower these dialects into Circt as before. And what was nice here is that you can also do some specific transformation at the Torch dialect level. So for example, you could do some consideration, some transformation with a high level of abstraction here. So this is exactly what I needed to try to generate hardware from PyTorch script. So I've added it on the flow. So now I have a PyTorch script. I go through Torch MLIR, I generate some core MLIR dialects, which are lowered into calyx, feed it into the calyx compiler, and then I go back to hardware dialects and generate verilog. So it's similar flow than before, we just start from PyTorch. Problem arrives quite quickly. So Torch MLIR generates some linear algebra dialect, and from that point, I'm supposed to call a function which is called the lower linear algebra, which gets rid of linear algebra dialect, but it was not working. So after the pass, the linear algebra operation was still there. I don't know why. I never understood. So it was, I tried tens of different functions to lower linear algebra into different things. So not only the arith or affine things, there are like 3 or 4 different lowering transformations to get rid of them, but that every time it was still there. So I guess that they were embedded inside a function or an object which was not handled by the tools, and then the lower ring was not done, but I don't know why. So I got stuck there, and I tried to find the solution. So I found another tool which advertised the same thing. So it was called CAD-HLS. It's from a paper, and the idea was to do some HLS inside Circt and MLIR. So this is what I wanted to do. So I tried it also, and the idea advertised in the paper was to do some PyTorch things. The same path than before, you generate some linear algebra things between others, you lower it into affine, and then you have a special dialect for representing C++ with HLS annotation. Fine. So this is a similar flow than what I wanted to do. The bad side was that once you've generated some HLS compatible dialect, you cannot lower directly into another Circt framework. It was not implemented yet, just advertised in the paper. So you had to re-emit C++. But the flow is working fine. So with the same PyTorch script, with the same flow, this one was able to lower the linear algebra operation. So I guess that was just a mistake from my part before. And inside this flow, it was working fine. So, okay, perfect. I generated an IR with an intermediate representation, which represents my PyTorch script as a set of for loops, and I regenerate C++, and this C++ code is correct and can be fed into commercial tools. But it's not better than before, but now the C++ code is working. So I try to reinsert it inside the flow that I had before to go into Verilog. So I give it to Polygeist, same issue than before. It generates AP ints. So it's like AC int, but for VT things. So, okay, as it generated code, I can modify the scale-HLS backend to get rid of AP ints. It was quite simple. So I generate int, short, and char instead. That was simple. Then I managed to go into upstream MLIR, and I want to go into the Calix dialects. Okay, some of the operations were not implemented in the lowering transformation. I could not lower if and select operations I had. But as I had the intermediate representation in plain text, I could modify the intermediate file, and to remove those, there were two instances of this operation. So I just translated them manually. I managed to go inside Calix and to do the transformation in Calix. And then when I wanted to get outside of Calix to go back into the core MLIR dialects, I found several tens of sign extension operations which were not implemented in for going from Calix dialects into core dialects. And there was like at every line a sign extension that cannot be lowered. So it was too much for me.
But they exist. Oh, okay. They exist in LLVM, of course.
Yes, they exist in Calix intermediate representation in their tool. They implemented it in their dialect, but they have not implemented the transformation for lowering it into existing Circt dialects. So maybe because they've never met them before, maybe because it's work in progress. Nothing of that is already finished. So it was too much for me, and I do not want it to modify tens of lines for removing them.
And you don't try to make like your ints unsigned.
Yeah,
Yes.
We do the ugly hack that you did for the.
Yeah, but this one was too ugly for me.
Because sign extension is a fairly trivial thing. You didn't even consider to fix Calix.
Oh, that's good.
Calix is written in Rust, and it's completely different.
Yeah.
It's completely different.
It's not something inside Circt, just there is a path from going outside of Circt doing the Calix transformation and turning back into Circt. I could have tried it, and certainly,
But it's, yeah,
if I want to use that for real, I will have to fix it at some point.
but you need another.
And I think the easiest thing to do was to implement the lowering inside the tool. Not that difficult. So to conclude, that was kind of fun. Circt is, there are many different dialects. It's not that simple to use. It's not that simple to decide which dialects you will go through. When you come from the outside, you just see a lot of dialects, a lot of errors, a lot of lowering transformation, and it's almost impossible to decide where to go through. So you find some projects that automate some things. You find that some papers where sometimes you find the code attached. So you can find some ways to do things, but it's still complex to use. Things are moving fast. So for these experiments, I had to compile like 4 or 5 times LLVM with different versions. So on the GitHub, you say that you work with that Git commit of LLVM. So I had one LLVM for Polygeist, one LLVM for Circt, one LLVM for scale-HLS, one LLVM for. So at the end, I have 300 gigabytes of compiled code in my machine for different versions of MLIR working sometimes together. And I had to go through a different repository to find some things that will do my lowering transformation. So I think there are many interesting things. The good thing, maybe, even if I'm in the bad schedule. It's open source, so when I face a problem, I can modify the code and add some fix to make it work. We have plain text intermediate representation at between each pass, so you can see what works, what doesn't, and you can modify it if you want. So you can try to understand what is done by the compiler. That's much better than commercial black box tools. And I also have to say that I think many paths for Circt are working, and I was trying to do HLS, which is not the main purpose of the tool. So I think that's why I got so many issues. I think that everything which is used to lower chisel into Verilog is working perfectly, and this is not what I've seen, what I've met there. So even if there are many bad sides in the tool, I think it's just because it's moving fast, because it's moving. So I think it will be interesting maybe in a few years. Maybe if I spend more time understanding exactly what I have to do to go through these IRs, will be a valuable tool and use it. Thank you.